Yeah, perfect.
And that's the way it works.
Okay.
So what are we working on today?
Alright, so I started probability and statistics.
Okay.
So, let's see here. Should I send you a picture of the problem?
That might be the best thing to do. Yeah.
Okay.
Go ahead. You have my email? Or if you just put DA, it'll probably come up.
Alright. Okay.
This is definitely probability and statistics for everybody.
Yeah.
I will be honest, is not my strongest suit. It depends on how complicated they are.
Oh, really?
Well, one of the few courses that I don't, in fact, the only math course I know of that I do not tutor is the probability and statistics course, the complete course. I certainly have been working with students on the probability and statistics that they get in, Algebra 2 and pre-calc.
Oh, okay.
So I know a little bit, but.
Okay, so I sent it to you.
All right, let me open it up, see what we're looking at here. It's not probability density function, is it?
No, I don't think so.
Okay, that's more towards calculus, but you send it to David Cowan, 1949?
Yeah, it's still sending.
Okay, all right. So what kind of problems are we looking at here? Is there one you can verbalize while we're... it must have just come in. My phone gets it before my computer shows it. Whistles at me. Just this one page?
Mm-hmm.
All right, I can probably handle these. Yeah, maybe. We'll start with, well, let's see. Where do you want to start?
Top of the page, probably.
Well, oh, okay.
No?
Yeah, no, that's good. These are examples, so I figured they would probably have explanations with them already. But okay, a card is randomly selected from a deck of 52 cards. What's the probability that a 10 or a face card comes up?
Mm-hmm.
Well, probability is all about successful divided by total possible.
Okay.
So how many ways are there to get success? How many 10s are in the deck?
4.
How many jacks?
That's 4 too.
Queens are face cards. Kings are face cards. So how many cards represent successes? 16 divided by 52 is the total possible chances, and so it's 16 over 52, which is what? 1/4? No? Let's see, it's 8/26, 4/13.
Okay.
Okay. The card is selected. What's the probability that it's a face card or a spade?
Yes.
How many face cards are there?
That's 12.
Okay. How many spades are there?
It's 4.
No, there's...
Oh, sorry. That's 12.
There's 13 of each suit.
Oh, okay.
In other words, there's 13 spades, hearts, diamonds, and clubs. This is one area of probability I know a lot about. Playing cards. I've played cards my whole life. So there's 13 spades, but 4 of those or 3 of those spades, the jack of spades, the queen of spades, and the king of spades, we already counted when we came up with 12.
Okay.
So there are only 10 spades outside of the face cards.
Okay.
So the total is 22 divided by 52.
All right.
11/26. Now, had they said a face card and a spade, what would that be?
That would be 3 out of... Wait, no.
No, you're right. There's only 3 cards in the deck that are both face cards and spades. And that's jack of spades, queen of spades, and king of spades.
Okay.
Okay. All right. Draw a Venn diagram that relates the 2 events, then decide whether the events are disjoining or overlapping. Okay. The result is an even number. The result is an odd number. Should those be separate like I've drawn them or overlapping?
Overlapping.
Oops, my bad. Result is an even number. The event B is the prime number.
Okay.
That's what you get when you take things for granted. Just assumed that it was going to say odd. But it doesn't. It says prime. Are those overlapping, and why?
Yes.
How much? How much is in the overlap area? How many numbers?
Even, I don't know.
Even numbers is 2, 4, 6, out to infinity.
Yeah.
What are prime numbers?
Prime is 1, 3,
No?
5. No?
2,
Oh.
3, 5. 1 is not considered prime, but 2 is, because the definition of prime is being divisible only by 1 and itself.
Oh. Okay.
And 2 fits that, because there's no other factors of 2 other than 1 and 2. So 2 is the only even prime number.
Okay.
So that is the only number that goes in there.
All right.
So those are overlapping. All right, now let's look at the result is 2 or 4. I won't draw it this time. I'll let you figure it out. And the result is an odd number.
Okay, so those are not overlapping.
Correct. So here we want the probability of A, probability of B, probability of A and B, or the probability of A or B.
Okay.
Result is an even number. Result is a prime number. We already know they overlap.
Mm-hmm.
How many items are in the even number?
2, 4, and 6.
Sorry, that last one I said it went out to infinity. I forgot we were dealing with a die. It only has 6 numbers on it. Okay. And the prime numbers that
2, 3, and 5.
Yeah, 2, 3, and 5 only.
All right.
So the probability of an even number is, in other words, the probability of A. What?
2 out of 6. I mean 3 out of 6.
So 1/2.
Yeah.
Probability of B.
Same.
Probability of B and A
B
is
and
the
A.
union, the overlap.
Oh, okay, so 1 out of 6.
There's only one die that fits that, and that's 2. And then the probability of B or A.
That's 5 out of, no, yeah, 5 out of 6.
And the probability of B or A is the numbers that occupy this area of your Venn diagram and this area.
Okay.
Or the total 2 sets minus the overlap.
All right.
Well, your total sets here, each one of them had 3 numbers in them. So the total was 6, and there was 1 in the overlap. So when you do B or A, it's the probability of B plus the probability of A minus the probability of their union.
Okay.
Okay, let's do the same thing with number B. Result is 2 or 4 for A, so probability of A is what?
2 or 4, so that's 2 out of 6.
Probability of B?
B is 3 out of 6.
Probability of A plus B?
That's 0%.
That means the probability of A and B, you're right. What's that thinking? And the probability of A or B, yeah, this is, in other words, this is the overlap, and there's no overlap here.
Okay.
But what's the probability of B or A?
B or A, that's all of them, right?
No?
No.
What that's going to be, if there's no overlap, then that's going to be the probability of A plus the probability of B.
Okay.
1/3 plus 1/2.
5 over
5
6.
over 6, yeah. And part of the reason of doing this with a simple situation like a die is that it allows you to come up with the algebra, kind of. In other words,
Okay.
B or A is this plus that. As long as there's no overlapping. If there's overlapping, then it's that plus that minus that. Actually, you know what? It's that plus that minus that, whether there's no overlapping or not. We can say the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A plus B.
Okay.
And that works. There's your algebra right there.
All right.
And in this case, plus B was 0, so. All right. Well, those weren't terribly hard. You have other problems? Are they?
Yeah.
Can you send them? We still have 15 minutes. It might be worth sending them.
Yeah, I can send them.
Okay. Basic probability is really quite fun and quite interesting.
Yeah.
Just that it can get hard really quick.
Yeah.
Were you able to have a look at the video from the previous session?
The video. Yeah, I did actually.
Yeah, I sent you that link. I just want to make sure it worked for you.
Yeah, it worked.
Okay. I might actually have this review session up by tonight, only because I can start the processing as soon as we're done, and then I can probably get it uploaded in a few hours.
Okay.
Looks like I heard another whistle. You must have sent it. Have you ever done any kind of online tutoring before, Emma?
No,
First shot?
not really.
Yeah.
Yeah.
What do you think? Do you think it's any less valuable than in person?
No, I really like it.
Yeah. It's hard to, you miss a few nuances sometimes, but you don't miss a lot.
Yeah.
Okay, we have 113 are either varsity or on the honor roll, 74 who are varsity, and seniors who are on the honor roll. What's the probability that the randomly selected senior is both a varsity athlete and on the honor roll? So, let's draw a Venn diagram, just
Okay.
to think about it. How many categories do we have here? We have 200 students. So when we have stuff like this, I like to draw a rectangle around the Venn diagrams.
Okay.
Because there's going to be some that aren't in either, perhaps. 113 students are either varsity or on the honor roll. There's varsity, there's honor roll.
Okay.
Either one or the other. There are 74 seniors who are varsity athletes and 51 seniors who are on the honor roll. So I can say that's 74, and that excludes the overlap. In other words, there are specifically 74 who are varsity. Now, hold on, that includes the overlap. And 51 on the honor roll.
Okay.
113 students are either varsity or on the honor roll. Does that tell us how many are in the overlap?
No, because they're not.
It does. In other words,
Oh, it does?
yeah, if we total these, we get 125.
Okay.
So there clearly has to be some on the overlap, right?
Okay.
Because they said that there's only 113 that are either varsity or on the honor roll. Which means that if I shade it in everywhere where it's not the overlap, that has to total 113.
Okay.
Which tells us the overlap. There's 12 that are both.
Okay.
So now we can fill in everything. We know there's 12 there. There are 62 here.
Okay.
And there are 39 here. In other words, that should total 125.
Okay.
Or 100 and, I did my math wrong. Let's see, 74 minus 12 is 62. 51 minus 12 is 39. That would give you 51 who are on the honor roll. It would give you 74 who are seniors who are varsity. Yeah, that's right.
Okay.
So 62 and 39 are 101 plus 12, 113. Something's wrong. Well, let's see. What's the probability that a randomly selected senior is both a varsity athlete and on the honor roll? Well, it looks to me like 12 out of how many? Yeah, 12 out of, how many randomly selected seniors? There's 200. So, the reason I drew a rectangle around this is because there's 200, so there must be 77 that are on neither.
Okay.
In other words, your totals have to total, not 77, 87. If there's 113 students are either varsity or on the honor roll, then there's 87 that are on neither.
Okay.
Okay? And yeah, this fits everything.
Okay.
And this Venn diagram was kind of needed to figure out what the overlap was. Oh, I know where I got that 125. That 125 is a fake number. That's just the total number of varsity athletes and the total number of the honor roll. But that doesn't really show up in a detailed Venn diagram. In other words, a detailed Venn diagram, when you label this number right here, you're labeling what's, I suppose it's by convention, but when I do it, I'm labeling what's only on the varsity. And this 39 is what's only on the honor roll.
Okay.
There's 12 more students on the honor roll, and there's 12 more students on the varsity that are also on the honor roll.
Okay.
All right. So that answer would be 12 200ths, 600ths, 350ths.
Okay.
Okay, let's see. Well, again, let's draw some Venn diagrams. I think this might work. I don't know. Venn diagrams,
Okay.
they're kind of tough. You have to develop kind of a knack for working with them. So let's see. We have a test 98% accurate for people who have the disease. So this is they have diabetes. 95% accurate for the people who do not know diabetes.
Okay.
I think we can say that, and we can say that. In other words, 2% of the people that have diabetes get the no diabetes diagnosis.
Okay.
Because it's only 98% accurate. So if you have the disease, 2% of the time you're going to get a result that says you do not have it.
Okay.
If you do not have the disease, 95% of those people are going to fall in this area, and 5% of them are going to get diagnosed as having diabetes.
Okay.
So, since the number of people that have diabetes is 8.3%, what is the probability that the diagnosis is correct? Well, if you have diabetes, it's 98%. If you don't have diabetes, it's 95%. So I think we would have to take 98 plus 95 and divide it by 200.
Okay.
Just right offhand, which gives you 193 over 200, which gives you 96.5%. And that seems reasonable, and I guess we could have gotten it, I'm not sure that's perfect, I'm not sure that's correct, but let me think about it for a second.
Okay.
It seems like it might be, oh no, hold on a second, let's see. No, we gotta weight it. Gotta weight it. In other words, we can't take a simple average of the 98% and the 95%. Because there's a whole lot more people that have no diabetes than there are people that have diabetes. Okay. So if you were to randomly sample 100 people, the 95% is going to be applied to 91.7% of them.
Okay.
In other words, this final number should come out closer to 95%, right? It should lean towards the 95% because there's so many more of them.
Okay.
So, I'm going to take a wild guess, but I think this is right. I'm going to multiply the 98% times the people who have diabetes, which is 0.083.
Okay.
And I'm going to add to that 91.7%.
Okay.
People that don't have diabetes, and they have a 95% chance of getting a correct diagnosis. In other words, this should act as a weighting factor. And now, if we divide that by 200, we should get a number a lot closer to 95%.
Okay.
Have a calculator?
Yeah, I do.
Let's leave these in percent and these in decimal, because we want a number that's in percent. This should be right.
Okay.
This should be right. And I'm going to divide that by, I don't need to divide that by 2. Hold on. No, I don't need to divide that by anything. That's going to be our answer.
Alrighty. I got 168.45.
Multiplied 0.98 times 0.083.
Yeah.
And add that to 0.917 times 0.95.
Here, I'll try it again.
Yeah, there's a mistake there somewhere. In other words, this number should be less than 1.
.95.
With decimals, I hope?
Yeah, 249.
There's the percent probability that the diagnosis is correct.
Okay.
And only because I weighted it. And this is a key thing, actually. When you start talking about expected value, you have to weight it by the number of people that are in the sample. It may not be exactly the way your teacher would explain this problem, but it's got to be pretty close.
Okay.
Well, unfortunately, I have another appointment to go to. Surprising.
Alrighty.
Sunday at 11, but we'll have to stop there.
Okay.
Yeah, problems like this are kind of cool, where 2 cards are selected from the deck and the first card is replaced before the second card is selected, but then the other situation is where the first is not replaced. In other words, the odds of me getting a king are 4 out of 52. But if I keep the king out of the deck and draw again, the odds of me getting a king are 3 out of 51. Now,
Yeah.
so the odds of getting 2 kings are 4 over 52 times 3 over 51. If you were to randomly be dealt 2 cards, that's the odds of getting 2 kings.
Okay.
All right. I will talk to you next time, Emma.
Okay, thank you.
Bye.